So today's topic is about big data engineering and scalable algorithm that can apply to it. So about me, I'm Felix Chen. I have 2 years of Hadoop experience. We mainly program on raw MapReduce API and Hive. I started to use Hadoop on 8-node cluster, and now I'm like managing and develop on 600 nodes, more than 600 nodes of cluster. At OpenX, we have 100 terabytes data every day. And our main business is to help publishers like BBC and the other websites that want to sell their ad to the actual advertiser like Coca-Cola. So we host an auction. The buyer like Coca-Cola bids on those auctions, and finally we get the winner, and then the publisher like BBC gets paid. So in order to host those auctions, we have a lot of events, and that is our data scale. So what is data engineering? People think data engineering and science like this way. For example, people think that engineering does use a duct tape to glue the fork to a cup. Like say your problem is to put your fork on your cup, and science may use like more clever way. Say this one you have a center of mass there, so it's inner in the cup, so it can hold. However, if you think in the other way, on the left you use the physics, on the right you use a duct tape, and you can think that those physics underneath is the algorithms. And on the right side, those frameworks and tools can help you quickly glue your fork to the cup. But when you master the physics, you can do more. For example, you can do bridges, buildings, cars, rockets. Each of those applications, you can think that is used to solve certain kind of problems. For example, building bridges to, you can cross a river. For buildings, you can have high density of people living in the same space. For cars, it's for transport. For rockets, you can explore the outer space. When you master the physics or the algorithms, you can solve more problem at larger scale. So this is actually the agenda of what I'll talk about today. I'll talk about like what kind of problems do we have, and then what kind of solution we currently have. Then I'll talk about those algorithms that can extend to your solution to solve more complicated problems. And those complicated problems can give you more business value. So what is our normal data engineering problems? Those people at YP probably have a lot of experience, the same as we are. Basically, we maintain the data flow. So starting from the first bullet is maintain the data flow. And the other things we need to maintain is data correctness, because you don't want to bill our customers with some wrong numbers, and which will cause a lot of trouble. And also we want to maintain our system stability. We don't want our system to fail all the day, and that will generally makes our job sucks, right? And what do we do in the data workflow? Basically, you can simplify that into a term that we use a lot, is ETL, extract, transform, load. And after so you extract the data from the raw format, you transform it, you do certain kind of operations, and finally you load to the system that can consume by the downstream. Downstream usually is like reporting that generates a report that we can bill the user, or like for internal analysis. And let's zoom in to this ETL process, like what is the normal thing we do in the ETL. Extract, transform, load. Basically, in extract, transform, load, we need to satisfy 3 things. First, we need to do deduping, or take off those bad data. Say, for example, if web traffic is bad, this is from a web bot or whatever, we want to take it off. And we want to join the relevant data. For this publisher and this buyer, we want to put them together. We don't want to put them separated away, then we don't know who to bill with. And finally, we want to generate aggregations. Aggregations, in short, is like from different perspectives. Say, for each of the buyer, we select several kind of properties, like for this buyer, how much we should bill them, And for each of the publisher, we want to select the value that we want to pay to them, right? So for each of those aggregations, it's pretty much like you have the raw data and then you finally get to like smaller chunk of value that is aggregated per buyer or per publisher. And usually we have like more aggregation that is like, it's tons of them. Yeah. So all the text above can be simplified, can be visualized in this graph. We have all the data coming in, we get it's joined to a large layer, and then we aggregate to all the downstream different kind of database or different tables. And then usually on the downstream, like this kind of database is usually more like a traditional relational database, and the downstream people would generate reports from those, like a monthly report, diagnostic report or whatever. And sometimes if you want to dig in more data science stuff, you may use an ad hoc query to directly query from your intermediate layer as well. However, doing ad hoc queries, it may be difficult. Like if you use the wrong dimension, which means like you want to see all the traffic or all the bidding events, like when the buyer trying to bid for each of the say we want to see the view of what really happened on each of the auction, then this kind of event level is too big and it may not be computable even if you have a really large cluster. To find those out, sometimes it's trivial, like you just look at the query, you know, but sometimes you wouldn't know. So we want to have an estimate. So this is another zoom in to this problem. We want to estimate for hard queries, for ad hoc queries. We want to estimate the probability of aggregation, which is the query that I said above. We want to see their cardinality. Say it's like the final row count for each of the query. We want to see their frequency distribution, like if the data is skewed, like if the data is having all the chunk of data go to one reducer, which may make the machine unable to compute. Also, we want to see what is the top K element. Like sometimes we don't care for each of the buyer. We want to know several buyers that bid the most, right? And we want to get those values out.
What is K?
Top K is like any kind of variable you can say, well, I want the top 100 users or top 100 things from my query. Yeah. And for those estimations, we don't have to be precise. We want this to be fast and stable. We want this like, even though the actual query is really hard to compute, but we can still able to process it when it is only an estimation. So for each of the problem, we actually have an algorithm for it. For cardinality, there's a popular method I'm going to talk about today is hyperlog. For frequency distribution, there's an algorithm called count-mean sketch and its variant called count sketch. For top K element, there's Lucy count, and there's a variety of families that can do this kind of in academia, they call it string summary. And for each of the algorithms, actually has really good runtime. Since it's, each of the elements can be joined together in MapReduce term is called combiner. It's usually can get O log n runtime. So even if you have your input set to be really, really large, it can run really fast. And better than that is it actually have the data size that only have several K bytes. What's the benefit for that? Say, in a MapReduce phase, on each of the mapper, if your data structure can be joined together, then actually it will produce really small data size and it will be kept in the memory. And after it goes to reducer phase, when it goes to reducer, if your data size is small, it's not necessary to be spilled into disk. It can still keep in memory. So, look, Ma, in memory computing, it's not necessary to use like the most fanciest tool out there in the industry, but like in traditionally people think that MapReduce is disk only and it is slow, but not necessarily. It actually runs pretty fast. Like in several seconds, you get your result. So let's zoom into this algorithm in particular. So what do we do in the cardinality test? The goal is to find out what is the distinct count for each of the elements. When we say the distinct count, it's basically like if you use, in terms of SQL, is select something grouped by several kind of columns. And when you group by several of the columns, you get the count of each of the distinct elements for those columns. Before we jump to the algorithm, let's talk about what kind of a naive approach you can do. Say if you want to count distinct elements, you just put it into a hash set. However, trivially, we won't have enough memory because you can't put everything to memory when you have big data, right? Another approach that is actually studied is called linear counting. The algorithm is basically, say, we hash the inputs and then we put it into a bit set. Like, if that bit is being set to 1 and you map to it, even if it is double counted, you use the rest of the, you use the whole bit set and estimate, like, what are the input sets. So basically, it's like a inverse problem. When you hash to something that has collision, can you estimate original count of the things? This can save you a lot of space, but not large enough, because from the study we found that we still need to keep the 1/10 of size of the input. That is too large, because like if you have 100 gigabytes, you still need like 10 gigabytes of memory to hold your input. So enter the log-log algorithm. The basic idea is we pick a hash function edge that map each of the n elements to at least log n bits. You can ignore the log n part. We just think that it's mapped an input into a random bit string. And for each of the bits, bit string, that is the A. That is X is your input from the n elements, and then you get the A that is the bit string. And let A be the number of the trailing zeros. Say, for example, I don't have the example, it's on the later slide actually. Say this is A, and for this one, the trailing zeros is 2. So let me jump back. And the algorithm goes like, you record the R that is the maximum trailing zeros you have seen. You will see 2 zeros in this time, and then you see 4 on the next time you record 4. You see 3 at the next time you still have the largest number 4. What can this give us to me? This is a strong statement that the cardinality is 2 to the power of R. And what is the data size that you need to store for R? Since R is just a count, you only need like an integer size, maybe 4 bytes or 8 bytes, and this is a really, really small data size to store the R. For all the A and all the input data, it can be thrown away. You only need to keep the number R. That is so far the largest trailing zeros you have seen. So why does this work? I have an illustration for this. Say you have n elements, and you have total of n distinct counts, and this n is a number that we want to find. So the array function maps the hash bit into the count of the trailing zeros. For here is 2. So in order for the probability of an event that RA equals to 2 is 1/4, because you need at least 2 of the 0 in the event that stick together to have that. If you have a lot of zeros happening at the same time, you actually have the event, say here is like 12 zeros. For this event to happen, the probability is actually 1/2 power to the 12. And that's like really, really small probability that you'll see this kind of hashing value to actually happen. So the how many inputs you have from the n to actually see this kind of inputs, this kind of hash value to happen, actually you need equally amounts of the input to actually have this event to happen. So that's why we have 2 to the 12 distinct elements to happen to have these events really happen. However, that's 2 to the R is a really, really bad estimation, right? Like it's generally bad that it's an estimate that is too rough. So if we have a lot of hash functions, or if you partition your sample size and get each of the large R we have seen so far, you can actually have a formula that can estimate the actual cardinality. And this formula is well studied and well proved, and some of the other algorithms have improved on this to make your estimation to be really precise and still store a really, really small kilobytes of data. And this is the original paper for this algorithm. So we have too many technical parts. Now I'm going to talk about the applications. There are a lot of implementations, and so far, what I found that is the best is developed by Aggregate Knowledges. So they developed a Java version, a JavaScript version, and a Postgres version, and they also defined a schema for the actual that large R that will convert it to a binary format that's can be parsed by all 3 kinds of libraries. There are also another popular implementation is developed by AtList. It's called Streamlit. It actually has a lot of different probabilistic algorithms implemented. Be sure to check it out. And also there are the others, like SuperLogLog is another paper published that uses a different improvements based on the original log-log algorithm. And based on the Java implementation, during the weekend I developed a demo that's basically this is a program that runs on Hive. So for this hyperlog to work, you just load the function in, and then for example, you want to estimate the cardinality, like for select whatever from source group by column 1 and column 2. You just use select column 1, column 2, and then this will return a struct, and you just ask for its cardinality, and then it will just return you the estimated cardinality for it. Also, you can output the temporary output, because each of the hyperlog binary output for that large R that we have seen, it's you always can go to if you have another large R, you can just get the largest R from all the different inputs, right? So if you cache the temporary output, say in this example is you get the input table, and then for a certain hour, you just insert it into another table. So you have original inputs mapped to each of the hyperlog format, and later on, it can be aggregated again. From the cache layer, you just select it from the hyperlog cache, and then you will have the cardinality for each of the hour. How can this help you? The last one probably is not that important. Say this. So I'm talking. I'll talk about like its application. Say we want to count the distinct users every hour. Like in this website, how many users did I have in this hour? Like even if they double click or whatever, I just want to know how many users in this hour we had for each of the hour, or even each of the minutes. Then we can ask like, how many unique users do we have every day, week, or month? For the second question, you don't need to scan through all of your data in week or month, which usually will take too much I/O and it will just take a lot of time to compute. Now you have your cached hyperlog intermediate format that you can just sum union of those hyperlog value, and then you have your cardinality which is like the unique user count weekly, monthly, or even yearly. And when you have the distinct counts, you can know the churn rate. Like for this days of user, how many of them have entered to the next day? Did they stick on my website? since each of the distinct counts can be union, then you can, when you have the union count, you can have the intersection count. So having a union, say you have the first day that is A, the second day that is B, you just calculate the counts A plus B minus the union, you get the A and B intersection, which is a user that stick to the next day. And if that number is high, you know that your website is doing well because people like to stick with your website. And since all the data is so small, you can just put it into your browser or put it into any kind of analytical software that can aggregate through years, which is almost impossible to do in many of the current platforms. So so that is the basic agenda that I have to walk through. We have the problem, we have the solution. Once we have the algorithm that can extend the solutions, we can extend to more unsolvable problem that previously is hard to compute, like the stickiness across years. That is really, really hard because usually there are too many data that you need to scan through to see, does this user retain to the next year or whatever? But now with Hyperlog, all of those become possible. And moreover, this is just one algorithm. There are way more different kinds of algorithms that you can actually use. Say for the algorithm that is similar to those are count-mean sketch, which can do frequency estimation, Bloom filter, that is a probabilistic set that we use intensively at OpenX, LucyCount, which will do the top k elements, and also sometimes we want to know the data skewing, which is like estimate the second order moments, or there are other algorithms that can estimate the entropy of your data set, like if everything is normally distributed, like evenly distributed, or if there are peak spikes in your data set, there are different kinds of algorithms can estimate your data property without really high data computational costs. Furthermore, if you have good algorithm, you can extend your problem set as well. So, for example, those are the highlights that I found that's extremely interesting are locality-sensitive hashing, which can find the similar items that is normally really hard to compute. ECLAT is a vertical format that an algorithm that can solve the frequency item set. Frequent item set is, say you have a market basket, and each of the baskets has several items you purchased. And from study, people found that if you buy diaper, you probably will buy beer. Why is that? Maybe it's because if you have diapers, it means you have babies at home. You have babies at home, which means you cannot go out to a bar and buy the beer there, so you have to buy the beer at your home to drink it yourself. And this kind of explanation is easy, but what if the combination of those items to the other item is not trivial? Finding frequent item sets is one kind of solution for that, and it's also applied to a lot of data mining problems already, like in DNA sequence finding, like for this, or even for proteins. When I have those proteins, I see another protein. They have some associations. Those kind of problems are hard, and sometimes it will be NP hard. However, when you have good algorithms, that is like, actually there are a lot of studies in academia fields addressing those kind of problems, and like if you apply those to business, it can give you a lot of business value. Also, there's another algorithm called BigClaim, and it's developed by Stanford, and it is used for graph clustering. Say, if you have like limited steps to compute each of the elements in the graph, that is also a really interesting problem because, say, actually, I can give you an interesting example of combining locality-sensitive hashing and BigClaim. Say you only know each of the, you have inputs of different users. Different users have different properties, and you know what kind of properties make different users to be close. They are similar. And when they are similar, you want to link them together. when they link together, it's kind of becoming a large graph. Now you want to see what kind of user group do we have in this graph. And mining a graph that gives you the cluster of different users in the graph is more efficient than mapping each of the users to a Euclidean space and use the machine learning clustering algorithm to do it. So like combining different sets of fancy algorithms, you can actually do some kind of problem that was traditionally really hard to do. So one more thing is like if you feel excited of those different algorithms and what kind of data scale at OpenX, we are hiring. Yeah. So this is the end of my talk. Oh yeah, for the clustering we have for the hiring we have the contacts here. I'll upload this to our website, to the Meetup page. So if you have any questions, you can, or you want to apply to OpenX, you have the contacts here. And next is questions.
It'd be nice.